Welcome everyone to the 15th Tea Talk. It will be a very interesting talk. I'm pretty sure near real-time river health monitoring from space. It's being presented by Dr. Bhabagrahi Sahoo, who is an associate professor at IIT Kharagpur. I don't have to go any further because his bio speaks of his accomplishments. So without further ado, let me hand over the presentation to Dr. Sahu. Dr. Sahu, please go ahead.
Yeah, thank you. Thank you so much, sir. So good evening, everybody. So I'll be presenting the presentation, this near real-time river health monitoring from space. So when I'm telling this is from space, that means I'll be using the images from satellite images like remote sensing images. And when talk about river health, because nowadays you can see river health is an issue. There is a issue of water quantity and quality. When talk about water quality, everywhere you will see pollution is there. And this pollution is the concentration is increasing because of less flow in the river. Because you will see after damming the river, at the downstream there is very less flow. And that is also increasing the concentration of the pollutants. So that's we talk about nowadays the concept of ecological flow or environmental flow. So that we generally derive from the flow duration curves. So all the things generally many times you can see this water quality, whatever is there, measured by Central Water Pollution Control Board or maybe State Pollution Control Board. They are mostly at maybe 15 daily scale or monthly scale. Mostly many of the things are at 3 monthly scale. So that doesn't talk about what is the water quality and how it whether it is usable for irrigation or maybe it is usable for drinking water supply. Then we don't have much data also like flow data in Indian river basins. Maybe when there is a gauging station, so they are the Central Water Commission, maybe state irrigation departments, they are measuring this particularly flow values. But if we talk about different locations along the river, so how the flow varies, so we don't have any data. So in that case, we generally many times we use the hydrology like we studied in our BTech and also in masters that the different routing models are available. The common thing that very simple is our Muskingum model. We know that. So those type of routing techniques we use, but for that we need also the river cross section data. Then we need the flow data, specifically at the upstream reaches and the downstream reaches. But those type of data is not available. So in a real time, when we talk about real time means in near real time. Real time means all of a sudden, suppose I will get the data and suddenly I will get the say remote sensing data. I will get the flow value or maybe pollution value. So, but that is not possible because there is some processing time involved in getting this remote sensing data, and we have to process that in our GIS platform. So for that we take some time. So that's why I'm calling it near real time. So when talking about near real time means I am talking about at everyday basis, and at 30-meter resolution. 30-meter spatial resolution is at 30-meter interval along the river profile. I can get how much is the flow value and how much is the pollution. So when I'm talking about pollution means it is total suspended solids, turbidity, then some of the heavy metals. So for this, actually this is from one DST project. So we got one DST project, and from that we try to experiment this. And this technique is mostly new in national as well as international area. So here we selected two rivers. One is the Hooghly River near the Krinseri Temple here in Kolkata, Howrah, and another is the Brahmani River. So because the Talcher Janapur is that is mostly polluted river is, so we used that two reaches. And the stream flow I'm talking about 30-meter spatial resolution and daily scale, as well as pollution is TSS turbidity and heavy metal. So we can monitor at every 30-minute and daily basis. So that will be helping us in taking some management decisions for our maybe river basin planning management or maybe water supply schemes. All those things we can take decision based on that. So my first part is assessing the river discharge using remote sensing. So for that we used the MODIS data. So this MODIS is the moderate resolution imaging spectroradiometer. So this is satellite information which is freely available in the public domain, and the special resolution 250 meter. That means one pixel is having 250 meter by 250 meter resolution, and we can get this data at a daily basis. So when I'm using this data, I'm telling it as a model. Mod is coming from Modis. And another model we develop, because this is at 250 meter resolution. So because if the river width is less than 250 meter, then it will make a problem, because one pixel will be coming inside the river, the water pixel, and another may come outside of the river water. So there will be land contamination. So the reflectance level will change. So how we are getting the reflectances? So generally we are coming from the solar radiation. So when the solar radiation falls on the water, so some of the particles, like maybe these sediments or some other things are there, so that on that the pollutions they get absorbed. So when they get absorbed, so some amount of energy of the solar radiation, we call it as high energy or high frequency radiations. So they get absorbed, and some are getting reflected back to the atmosphere. Then in the atmosphere also some absorption is there. So after that, some amount of energy go into the that is satellite. So there they have the satellite sensors are there, cameras are there. So they can record those reflectances. So in that way, you can see there's a damping effect. That means what are the solar radiation falling on the river water, some are getting absorbed and less is reflected back. So we call it as long wave radiation, because some energy is getting absorbed, so frequency reduced. So because of that, you are getting long wave radiations. We know that if frequency is more, the wavelength increases. So what if the water river width is 250 meter, less than 250 meter. So in that case, we may get land contamination. Land means there is a sand, although things in the riparian zone. So the reflectance may be higher. The water generally try to absorb more radiation. So reflectance will be less. And when we're using the fusion model, so it includes the MODIS and Landsat data. So Landsat is having 30 meter resolution pixel size. So it is having better resolution, but the revisit period of the satellite is 16 days. That means at every 16 days, I will get only the remote sensing data. So if I want to estimate that at every daily scale, so I cannot use this Landsat data directly. So what we do here, we generally fuse this MODIS model with the Landsat data, MODIS satellite data with Landsat remote sensing data, so that I can generate at 30 meter and daily scale reflectances. And I can use that in my model, so that I'm calling it as fusion model. Then we used one probability statistical model that is called a COPLA, but is very it involves the marginal distribution, joint probability distribution. Then we developed the CFOS model. C for that is COPLA, and FOS means that is the fusion model. So the concept here you can see in this picture. When there is satellite here, so we have the land pixel. From the lands, we'll be getting one land pixel, and from the water, you will be having the land water pixel. So more radiation will be absorbed by this water, so that the reflectance will be less. But if I'm choosing any urban pixels, urban land use, maybe on the rooftop or something like that. So in that case, you can see the change of reflectance level in a day doesn't change significantly. But in case water pixel, if the water level increases, so more radiation will be absorbed. So by that way, the reflectance will be less. So in that case, you can see if I'll be plotting this with respect to in the x-axis time versus in the y-axis the W pixel, that is the water pixel reflectances, and see the land pixel. So land pixel will be almost constant. Although it is not 100% constant, it is almost constant. And comparatively, you can see with the change in water level, the increase in water level, the reflectance level of the W pixel will be decreasing. So if I'll be doing C by W ratio, and I can link with that discharge, so I can get a relationship between the C by W pixel as well as the discharge. And by knowing this remote sensing pixels like C and W pixel, so I can estimate what is the discharge level. So in this case, why we are generally making a division of that? Generally, what happens when the solar radiation falls on this ground, I just told that some amount of energy is getting absorbed by this atmosphere, because there is some atmosphere effect. Maybe there is the dust particles are there, maybe pollution is there, so they may get absorb some energy or radiation. So because of that, in one, say we can say it is seen that around 50 square kilometer of area, the disturbance is almost similar. So if we'll divide this C by W, so the atmospheric effect can be neglected. So some amount of noise is there in the C pixel, some amount of noise is there in the W pixel. So by that, if we'll divide it, so it get mostly cancel out. So that's why we are relating this Q, that is discharge, with respect to the C by W pixel. But if there is a cloud, because what I'm talking about here all are mostly dealing with the visual range of electromagnetic spectrum, that we call the optical remote sensing. So here we use, in case of discharge, we use the NIR band, near infrared band. So when there is a cloud contamination, you can see the C by W pixel, they behave abruptly. So in that case, you cannot use the C by W pixel. That's why this technique is not useful in case of if there is a cloud cover. And then what we did in a channel, we suppose this is 1 pixel. So we divide this width of the channel into different pixels. It is having equal to, maybe if you are talking about Landsat, then it is 30 meter by 30 meter resolution. So every 30 meter resolution will be getting small cube parcels of flow. And if you will take the pixels along this river width, so I'll get several number of pixels, and I can combine that. So that's why I'm taking a summation, and I just used one regression analysis, that is y equal to mx plus c type of relationship. And here we used this technique in case of Brahmani River, that is in the reach between Panpos to Jenapur, and we have taken 3 gauging stations for validation, calibration and validation. So Panpos, Gomlai and Jenapur, and for that we use the Modi's NR band 2. So in case of Modi, the 36 bands, so only we use the NR band 2, that is having the near infrared band, and it has a spectral resolution, that is the wavelength is 841 to 876 nanometer, and spatial resolution 250 meter, and 1 day temporal resolution, because every day it passes through that place. The Landsat is having that is NR band 5, so it has 11 bands. So out of that, so band number 5 we are using, and it has a similar type of spectral resolution 851 to 879, having 30 meter resolution, and we are using the fusion of these two. So note that the spectral fusion is possible only if there are almost similar type of spectral resolutions. So these are some of the techniques we use for this. That is one equal image processing, downloading the image, just cutting that image from that you call clipping that image. Then we do for reprojection. I'm skipping these slides, so this is not much useful because it's not too much general. Then we try to select the cloud free images. So you can see in the left hand side, so the white pixels are mostly cloud contaminated. So if there is cloud, so reflectance, atmosphere reflectance will be more. So in that case, we'll be getting white patches type of thing. But in case of river, you'll be getting dark pixels, because mostly in case of river water, it absorbs all the energy. It just behaves similar to the something like black body. So less reflectance will be there, so we'll be getting black type of patches. Another technique is we have to use the box matrix, center matrix. That means if you have a gauging station here, so we have the flow data here. So this is around 50 square kilometer of area, and we try to get some urban pixels here, urban land use here, so that we try to, because these are different pixels. The dot points are talking about different pixels where we have the Landsat images or maybe Modi's images. So they have about 250 meter resolution for Modi's and 30 meter resolution for Landsat. So these pixels, that C by W pixel is, because this is the W pixel, water pixel, and this is the land pixel, that is C pixel. So we try to get the ratio for each and every pixel. W pixel is fixed, but C pixel is varying. So where the correlation is the maximum with discharge, so we are selecting that pixel as the best urban pixel, and we consider that as the reference pixel where the reflectance level generally doesn't vary in a day. So that doesn't significantly vary in a day. Then we use some noise filter. This is called as trace filter. I'm not talking about that. Then we use the spectral algorithm developed for that. So we use the Q times the discharge time series versus the C by W ratio time series. And we develop some algorithms that is called a Coppola algorithm and a little bit non-linear type of thing. So if I'm directly taking the pixel values of Landsat and or maybe MODIS and directly correlating with the discharge pixel, then I will be getting less correlation. But if I'm using the C by W pixel and using some Coppola, the nonlinear type relationship, so it gives a better result. So what do we do in this fusion model? Because you see this MODIS pixel, we are getting daily MODIS data you are getting. So, but if Landsat, it has a review period of 16 days. So on the first day, so you have the Landsat data, but on the 16th day you have the Landsat data, but in between you don't have. So this is having 30-meter resolution. So what do we do? So corresponding each and every MODIS pixel or MODIS image, we can get the synthetic Landsat image or similar type of Landsat data, which is having every day and having 30-meter resolution. So that is the concept of this star FM algorithm. So this is a complex, you can see the CMOD and CFOS model. CMOD is the directly when using the MODIS data having 250-meter resolution, but CFOS is the 30-meter resolution. So you can see this is very complex type of model, the non-linear model. So if you know this, the pixel ratio, so directly I can estimate what is the Q value or discharge value at any gauging station. So this is for Janapur gauging station. So last plot I am talking about, this last one. So this is the CFOS model. You can see this is a scatter plot 1:1 line. So where it almost follows. Some deviations are there, but that means the efficiency is very high. If I'm using the remote sensing images and corresponding, I'm getting the Q value. So this is for both monsoon and non-monsoon flow we have estimated. So this is for Gomlai. So Gomlai, you can see it giving better result in the last the I'm talking about CFOS model last graph, and this is the last one also. This is for Panpos. So this is also giving better results. And then based on that, we can develop the flow derivation curves, and this is we can develop the different flow regimes. So I'm telling here high flow means it is around 20% exceedance probability. Then it is intermediate flow, it is up to 70%. Then low flows, it is up to 70 to 100%. But generally, when we talk about environmental flow, we generally consider the Q90 flow. That means corresponding to Q90 value, 90% probability, what is the flow? So that is the environmental flow. Generally, we have to release from the reservoirs, and that is a must for the sustenance of the downstream river ecosystem. So by that way, I can use the remote sensing tools to estimate the environmental flow regimes also. Then second part talks about the river pollution using remote sensing. So here we have used one site for Hooghly River, that is Dakshineswar and Howrah River, in between Dakshineswar and Howrah. And we have selected three sites. This is S1, S2, S3, and this is one drain. This is called Balikhal. So this is our most polluting drain here. So it is joining here. And if I can estimate what is the water pollution at this S1, S2, and S3 pixels, so even if any drain is joining there, so I can tell that this drain is generally polluting significantly, depending on this concentration of these two sites. And by that way, I can tell this is the contaminated site, or maybe this drain is polluting this river reach. And based on that, I can identify the area which is polluting, and I can go for any type of management or contaminated site management practices there. And for that, we have used red band. So in this case, in case of flow data, we use the NIR band, but in case of water quality, we use the red band spectrum. So red band, it is seen that red band is mostly correlating with this water pollution parameters. And for that, what we do for developing the model, we try to check what is the satellite revisit time. So generally, for every satellite, they have already published that the satellite will pass this area during this day and during this time, on this day and during this time. So based on that, we go to the river, inside the river, particularly in the middle of the river. You can see this is the boat. This is one of my student, that is Devi Prasad Sahu. He is also our CAETian. So we go into the river, the middle of the river. Then from there, we try to collect the water samples. Then what the water, automatic water quality sampler is also there. So by that we try to uh, estimate those samples, and for heavy metals, all those things, we try to collect these samples and we bring to the lab, and by using automatic observer spectrophotometer, so we try to get what is the heavy metal pollution uh, in this river. So we try to pinpoint what is the pixel, the latitude longitude of this pixel, and corresponding to that, what is the satellite pixel. So that means there is a one-to-one relationship. That means when the satellite passes, during that time we try to collect the water sample from this middle of the river, and that water sample is correlated with that specific satellite pixel, and based on that we develop the relationships. So again, this is again the C by W pixel matrix, so I'm not explaining again that one. So this is the site from where we collect the sample, and these are the urban pixels C1 to CX, and we try to get the correlation, the best correlation. We try to get what is the C by W pixel, like we did it for water quantity estimation. And this is the complex model we developed. So you can see this is for 3 sites. So VS is for virtual station 1, 2, and 3. So this is a very complex type of approaches. So if you know this ratio, C by W pixel, or maybe S by CB here I have used. CB is the generally the water pixel, uh, and S is the land pixel. So by that way we can develop the relationship. And this is for turbidity. So I know, and you can see these plots that are different times when the get continuous recording of these pollution levels for different locations. So this is the last one. So team battery. So this is for so this is also, you can see following the time series, you can see at different times I can get the data. So daily scale, and these are the measured values, observed values, which are at a discrete time scales at a longer time duration. So that means that every day I can tell that at this location, this TSS value is this much, or maybe turbidity value is this much. So by that we can develop the maps. So so the red is more like highest level, and green is the low level. So by that way you can see that
I think the voice dropped.
we use 2015 of state pollution.
I think there is some internet issue. Let's see if he joins back. Okay, he joined back. So let's see.
So I think there's some network issue, so it got disconnected automatically. So am I audible, sir? Hello, sir.
Yeah, you are audible. No problem.
I don't know where from where I dropped. Anyway.
Go back, I think. Uh, more. Uh, no. Uh, 25. I think 25 or 24. Uh, uh, I can't say because both. No, yeah, 25. 25. You dropped off at 25.
Yes.
Yeah.
Yes, sir. Okay, sir. So this shows the how the turbidity and the TSS they're varying along the ridge. So by this way we can map along the river ridge. So how the pollution level or maybe TSS and turbidity level is changing or varying along the river ridge. The third is the near real-time monitor heavy metal pollution from satellites. We used for particularly heavy metals, and we selected the river ridge from the Sangkoel river ridge to the Janapur of Brahmani basin, and the heavy metals I'm talking about here for iron, zinc, copper, chromium, lead, and cadmium. And for that, for testing purposes, we use the data of State Pollution Control Board data from 2007 to 2015. So these are different industries are there, and many more have also come by this time. So they are mostly polluting. So that's why generally these are the techniques by which we can trace that which industry is generally releasing this. Like for iron, 300 for zinc. Sir, am I audible?
Baba, continue.
Hello, sir.
Yeah. Yep. You are.
Actually, sir, this is unstable internet in the office. I mean, the office was still then. I don't know why it is happening. Yeah. So my slide is visible, sir.
No.
Now is it visible?
Yes.
Okay. So it shows also here you can see at the x-axis this is talks about the reach length from 0 to 320 kilometer along the Sankwal reach to Janapur. So this is on a specific day that is in January 2015. How it really varies. So how it is varies along the river is. So by that way you can know that how the contamination is there at each and every location along the river is. And this is the water quality mapping. So here you can see from Talche to Janapur for turbidity it is unsafe, it is greater than 5. TSS, it is some in some patches TSS is more and some are yellow, that means acceptable. Iron is, this is mostly contaminated by iron. Iron contamination is very high because it's, the HPA is greater than 300. Zinc, it is safe from zinc, it is less than 5,000. It is safe from chromium, safe from copper, but lead contamination is there, so it is greater than 10. Cadmium contamination is there, so greater than 3. So at different reaches, how it looks like. And here you can see the spatio-temporal distribution, how it is varying on a specific day, and along the river is how it is varying on that specific day. So we can use the remote sensing techniques by that way. And this is for the Talcher Janapur river reach, so different HPI values. So overall, you can say that many of the many parts of are mostly high to critical type of things for drinking water. So this is about my presentation. So thank you. Sorry for disturbance in between. So if you have any queries, please.
Yes, now thank you, Dr. Sahu. May I can now open it up for any questions anyone may have. I have a question. Why did you use red band for the TSS and turbidity, whereas you use near infrared for the water quantity or the depth?
Yes, sir. So red band in the visual spectrum, it is the wavelength is little less than the NIR band.
Correct.
So it comes around 800 to that is 600, 700. So this is 700 or 800, that is NIR band. And sorry, red band is just first red band, then NR band. So length is more. So it is seen that from literature, it is seen that red band is mostly correlating. So from the previous literature, we have seen that red band is mostly correlating. And we also tried with NR band. So in NR band, we are getting very less correlation. So that's why we are using this red band for water quality. We also tried for NR band.
I'm sorry?
We tried for NR band also, but sir, water quality is not giving better result.
I have a question, Dr. Sahu, and
Yes,
myself, Dr. P.K. Das.
Yes, sir.
Have you taken care of these perturbances like human interventions? Suppose there is a barrage gate operation and there is some disturbances and the flood are coming and there are sudden rages. Then what about the flora fauna in wetlands? Like have you taken care of environmental flow in Bhitarkanika, all that? It is coming under that Brahmani basin?
No, sir, Bhitarkanika I have not considered. Bhitarkanika I have not considered. But it talks about
environmental flow is necessary, and part of Brahmani river flows to Bhitarkanika.
Yes, sir. Yes, sir. Actually, sir, this is remote sensing. That means whatever reflectance is there, we are collecting from these remote sensing images, and corresponding to the what is the flow it is passing through that section. So we are trying to estimate. So by using that long-term data, this time series, from there we are using the flow division curve. And from that, the 90% exceedance probably whatever the flow we are getting, so that is corresponding to the environmental flow. So that's in our guideline. So that is the minimum flow we have to release from the reservoir, if there is a reservoir, or minimum flow should pass along the river reach so that the ecosystem will survive. So that we talk about environmental flow. So that is the Q90 flow, that is 90% exceedance probability. So if there is some flooding or any other thing, so naturally the perturbation will be there and the reflectance will change accordingly. So based on that, we can estimate what is the flow also.
Right. Okay. But you have taken river basin is very vast unit. What is the minimum unit you have taken so that you can conclude with a concrete suggestion you can give to a like a watershed or a sub basin, something like that? Have you studied that one?
So actually along the river it's every 30 meter, because it talks about 30 meter. At every 30 meter spatial resolution, that is 30 meter length, it can
No.
estimate
I'm not
how much
talking
is
of
the
that.
flow.
I'm not talking of pixels. I'm talking
sir.
of a unit, a hydrologic unit like let's say a watershed or a sub-basin, because Brahmani basin is too large to study all that. You can do it, but it takes time. But what about, have you studied one of the unit that you can conclude that these are the things and that has happened to that sub-basin? Such a result.
No, sir, we have not done much on application because we developed the technique here, but we are not go for much application of that.
How can you ensure that your technique is working or not?
No, we
How
have
to
tested because whatever
calibrate
the
that?
we have calibrated and valid that. Of course, that those plots I have already shown that scatter plot, all those things, how it is performing.
Okay, thank you, thank you. Very nice presentation. I thanks on my behalf.
Thank you, sir. Thank you, sir.
Okay, any other questions? Thank you, Deepak Babu. Actually, the other question I had, if nobody else is asking, I'll take liberty.
Yes, sir.
Nowadays we have artificial intelligence correlations, that can predict all of these instead of going for a Kapula, integration process.
Yes, sir.
So why have you tried some of that and seen if the
Yes, sir.
result?
Yes, sir. We have tried that. We have used the support vector machine, then random forest, Kapula. But we have seen that Copula and this support vector machine, they are giving almost similar type of results.
Correct.
But because in that thing we have to use the C by W pixels as input, not like C pixel and W pixel. So this I mean, because generally in case of machine learning also, they like this like garbage in equal to garbage out. So if the data pre-processing is not good, that the input data is not good, so even whatever the machine learning tool we can use, that may not perform. So that's why you have seen that whatever the input we are putting for Copula, so same input we are giving for this random forest and support vector machine, and we check that support vector machine is also almost giving a good result comparable to Copula.
I have used support vector machines and they are pretty robust. I mean, the way the support vector machines have been developed, they're pretty robust. And so why go for a Kapula type? Unless you want to publish a paper.
Yes, a Copula, because in that case we have some control on that. But support vector machine is just like you train that one and get. So by that way you can get what is the equation, the model, what is the nonlinear model, and you can directly use that. But in case of machine learning, so then you have to use that particular support vector machine always in that case.
Yeah, but Kapula, my argument is Kapula is making it rigid, more deterministic, as opposed to more stochastic. In case of, I know it's a black box, but there is some stochasticity in that. That
Yes,
when the machine learning learns the process, it will adapt to the process. Of course, as you said, it depends on data. Garbage in, garbage out can happen. But Kapula might be restricting. Kapula might be restricting some of your extremes. If which probably is captured by the support some machine learning algorithm. I'm not advocating support vectors, but
yes.
do you?
But I think again from that if you talk about deep learning tools like LSTM, nowadays LSTM is giving better results. So we have not tried LSTM. So I think LSTM can also give better results. be better option. But we are not
Yeah,
tried
no,
that.
I don't disagree with you on that. I'm just saying that if we want to make it a real time, as you said, or a near real time monitoring, using an easier algorithm that can produce results faster could be a better approach as opposed to going for a complex algorithm that might take some additional time to compute things, is what I'm kind of thinking here.
Yes, sir. Yes, sir. Yes, sir. Yes, sir. Yes, sir. Thank you.
Okay, well, my question is done. Excellent presentation, by the way. We missed out a bits and pieces from the when you went to the specific heavy metals. Okay, some slides were missing, in your presentation, but I think we can manage with what we saw. Okay, so any other questions from anybody else? Sushant, you want to ask a question?
Sir, actually, we are working together.
Oh, that doesn't mean that you
Dr.
cannot ask a question.
I know, sir. Myself, Dr. Chandana Chatterjee and Dr. Bhabagrahi Sahoo are in a group, in a consortia. So we are working on actually 2-3 basins. Like Bhabagrahi told, he has worked in Brahmani.
Yeah.
Chandranath and me are working for Mahanadi as well as for Krishna Basin together. So this covers actually identification of small water bodies. Like recently, Government of India has developed the water body sensors, but
Right.
actually it is really very crude if you will go through that document. So here actually in India, NRGS program, so small water bodies has been large number of millions of small water bodies have come up of the size from 10 meter by 10 meter to large size. So we have almost developed a methodology so that automatically it will extract all the small water bodies, and we have tested it in Niagara district already. And then we are now extrapolating for the whole basin, Mahanadi basin, so that all water bodies we will able to delineate, and then we will able to predict how much water we are really storing, because all our government is shouting that all water is being stored by Chhattisgarh and they are playing with us, because when they are releasing water from their side, we are facing a flood type of situation. And if they have go for n number of barrages also, absolutely no problem, because we could find that we have enough water in our area also, mid basin as well as lower Mahanadi basin. We have also enough input from rainfall, so that we can store, and we can also go for n number of structures instead of blaming government of Chhattisgarh that yes, why are you going for that? So keeping that in mind, we are working for last several years together. And we will be working together also. Similarly, Krishna actually is a deficit basin where the rainfall amount is very less, and there is a lot of problem is there also, the water scarcity. So that we have just initiated some of the work, and we will be continuing, sir.
Oh, good. No, I mean, these are very good work, and I'm very proud that CAETIANS are leading all this work. So that's a good, that's the best aspect of the thing. Any other questions? I know Sushanta didn't ask any, so I'm very disappointed. But Rama, there are Mahendra, Shreyasi. Who else is there? Anybody wants to ask a question or make a comment? Devi Prasad.
I have a question to Dr. Sushant. See, we are having Mahanadi, we are studying, we are having 52% of the catchment in other than Orissa state, like Chhattisgarh, and we have 48% of the catchment. And where is the problem? We have our catchment and we have our water. They are just storing their water in the barrages. We have not done barrages. It is our fault. We can store many. You can create the infrastructure to store. Your microphone is not on.
Sir, actually, could you able to hear me, sir? Deepak, sir?
Yeah.
Actually, sir, we are just trying to prove that hydrologically that even we have also enough water available for us, and if we wish, we can have more number of barrages and storage structures. But nowadays, maybe constructing big water storage structures will be difficult. But we can go for a large number of water bodies. You might be knowing Dr. Atmaram Mishra sir. He is a very senior person, and he retired as a director of our institute. So from his time also, we have standardized if the area is located in a particular location, how much percentage of area if we are converting for a water storage structure, how much will be able to store. So likewise, for us actually in delta area, even if we convert 20% of the geographical area into ponds, all will be filled. So this is the situation for Odisha. And in the middle portions, if 12 to 16% of land can be converted, we can store that much of water. Actually, Dr. Balaram Panigrahi sir is not there, but his PhD work was also on this. Similarly, for uplands, we can convert from 5 to 80% of land. So this is the potential of water storage which is possible in our state. We are not doing, and blaming Chhattisgarh is actually scientifically not required. They are doing their part in the upper Mahanadi. We are in the
going.
Yeah.
Thank you. We are going out of the topic of discussion. Thank you. Thank you very much. Now we can come back to again remote sensing. If anybody.
No problem. No problem. This is an engagement section. So anybody else? Shakti Prasad Das Babu, you wanted to ask a question? Okay. Well, I don't see anybody else.
Actually, sir, Deepak sir, all the analysis we are doing only in using remote sensing product only. Because that is the only thing which speaks about real time or with a little lagging. So we are only using remote sensing product only for all these analysis, along with the hydrologic data which we are collecting from Central Water Commission. Like, sir, why Bhabagrahi restricted his study to Janapur and Panpos is because all the gauging stations are there only. And if you ask about Bhitarkanika, there is no gauging station where we can get the discharge data. So that was the restriction. Similarly, for Mahanadi, beyond sir Noraj, nothing is there. So we will be only restricting our gauging stations beyond that till the top of that.
But what about the siltation activity that you are taking care of or not? I don't know. CWC, they are having every year they are taking a section. They take section and they correct it. But how you input that area in that phenomena in your satellite remote sensing model that you are doing? Every year there is siltation. Every year there is siltation.
Yes, yes, that suspended load we can do. This TSS turbidity, whatever we are estimating. So by that we are estimating. But if how the cross section is changing because of this siltation,
that is due to bad load only. That is due to bad load only.
Yes, sir, that is another study. So that is not related to this water quantity or quality. So that I didn't present actually. So that one of my MTech student is also doing. So that I didn't present. So we can use also by collecting the different digital elevation models and from that. But the accuracy is very less because if you will be using the LiDAR data, which is having 1 meter resolution, that is very good. But LiDAR data is very difficult to get. It's not free in India. So what are the free data is available? So that we are using actually make use of that.
How about INSAR?
Yes, sir. Yes.
Do you get a free INSAR data in India?
No, sir. Free data is not up. Nowadays they have made it free something like it will be more than maybe 10 meter resolution. I think they are just free some months back.
Oh, okay.
But not all data.
Can you stop sharing so that the screen? Yeah, please.
Okay.
Yeah,
okay.
Stop sharing. Yeah, thank you. So, any other questions from anybody else or any engagement comments?
This study mostly part of the Devi Prasad Sahoo, so he is already there. So he can comment. Devi, he is now in Italy doing his postdoc. These are also
good alumni.
Oh, hi, hello everyone. I'm Bhabagrahi Sahoo. Thank you, sir, for giving me the chance to talk. And this study is particularly based on the remote sensing based approach in India, because till now, from the PhD, I have not seen the optical remote sensing is being used to derive the discharge in India. And at the same time, although we have altimeters like the radar altimeters and the SAR at the INSAR, sir, you're right about the INSAR, because currently I'm using the INSAR for the Mackenzie rivers here, and also I'm using the INSAR for Danube. And currently I'm using also deriving the deltaic channel cross sections using the INSAR for the hydrodynamic model longitudinal profile derivations, and also including the SWOT observation to the INSAR. So this is actually if we adopt all those things in Indian catchments, so it will give us it can solve many purposes like the data scarce conditions when we are dealing with hydrological models and hydrodynamic models. We have a lot of data gaps, especially the dismissing of the gauging stations. So in that case, by adopting these techniques, that could help us to get the long-term discharge time series, or something around 20 years or 30 years. So that will give us a good observation of the basin with respect to the time, which will also help us in the climatological studies, like hydroclimatological studies. So this will help us to understand how the basin is behaving in last 2 decades, which is we may have the ideas about hydrological models, but if we use that remote sensing based techniques in these, including the hydrological models, we may have we may get over those conditions that we are going to face in India. Thank you.
Well,
I'll just add one thing, that people are now trying for drone survey and drone use of drones instead of satellite data, location specific. They can get actual the actual studies of those like you are doing through remote sensing. Drones are now used. Some people are actually trying for making those.
Yeah, concentrating on that, here in Italy, there is a project called OUAT, which is a project funded by this European Commissions. So what they are doing, they are integrating the drone observations with the satellite altimeters observations. So they have the drone observation at the same time of the altimeter observation, and they are correlating those observations to get to get the remote locations. How we can derive the remote locations observations from the satellite observations by correlating the drones with the satellite altimeters. So that is a good exercise, but that needs funds, of course.
Thank you.
Yeah, thank you, Debbie. Actually, I'm curious. Are you planning to come back and utilize some of your knowledge gained in Italy for the work in India?
Yeah, of course. Actually, I'm desperately trying to get into any organization if I got any chance. Actually, I have spent 1 year, and currently I'm involving in European Satellite Agency, the climate change initiative for discharge, like the CCI soil moisture that we in last 15 years we are dealing with the climate change initiative soil moisture products. So now we are involving currently. Now the paper will come. We are deriving the river discharge for worldwide river basins. So I'm quite curious about all those things. But if I'll get the chance in India, I'm desperately trying to come.
Yeah, no, yeah, great. Thank you. Okay, we just ran out of time, so I want to really tell you one thing, Debbie, is that Sushant Jana probably will be the next director of IIWM. Keep connection with him so that he can hire you. Okay.
Thank you, sir.
Thank you, Bhabagrahi. Sorry, I should say.
Thank you so much, sir.
Thank you very much. It was a very interesting presentation. One thing caught my attention, which I didn't ask because others were discussing, is lead pollution. There is a whole lot of lead pollution that you have shown, which is something that that needs attention. Okay,
Yes, sir.
and because lead is a poison, essentially poison. Okay, other heavy metals are that you are studying, but lead has a potential for a lot of issues. Okay, health issues. So thank you,
Yes, sir.
and very great presentation, and very proud of you of your work. With that,
Thank you so much, sir.
thank you. With that, I'm